So okay. All right, so then let's continue our class. So the same beam problem, exactly same, except that now we constrain one end. So this single beam, but we constrain one end. Okay, and then we are going to look at the eigenvalue problem. So we apply this boundary condition. So V1 and theta 1 equals 0. We apply that. Then what do we do in your equation of motion? What you have to do is simply delete those row and column. When you have a constraint, then delete those row and column, then you get only 2 by 2 matrix. That's what you have to do as you apply the boundary condition. Okay, so you have difference matrix like this, and then diagonal mass matrix and consistent mass matrix in this manner. Okay, so you got 2 by 2 out of 4 by 4, deleting those row and column. Then you do same eigenvalue calculation, such as this one, this calculation, except that previously this was 4 by 4, 4 by 4, but now this is 2 by 2, 2 by 2. So 2 by 2 equation, that means you're going to have a 2 eigenvalue and eigenvector. Okay, so this is eigenvalue using consistent mass matrix, and those are eigenvector. This is obviously V2 and theta 2, because V1 theta 1 is going to be 0. So in this case, you don't have 0 eigenvalues. Okay, because you fully constrain any rigid body motion. If you have 0 eigenvalue in here, then something is wrong in the formulation. Okay, so we don't have 0 eigenvalue. Then this is the first eigenvalue, second eigenvalue. So if you take a square root of that, that's going to be angular frequency, natural frequency first, and second angular natural frequency. And what about this one? And of course, you have to do this same thing as we did. You have to plug into here. In this case, this equals 0, this equals 0, so we don't have to worry about that one. Plugging this V2 and theta 2 and plot it, then this one is going to be, if you plot it, it's going to be like this. So this is 0, okay? And here you got negative 5, oops, negative 5, 8, 8, 8, okay? That's the displacement. And slope is also negative 809, this slope. And the graph, if you plot it properly, it's going to be like that. So that's the first mode, as you expect from the cantilever structure. Okay. And second one is 12, 12. And if you also plot that, then obviously qualitatively look the same, but if you plug into this expression, so that expression and plot it, then what is going to be the second one? What is the second mode shape? It's going to be like that, right? So that's going to be this one. And again, just looking at that, it's not clear, okay? Because they have a similar, characteristic, but you have to actually plug into here, right? Plug into here, then you're going to plot this one and that. So first mode and second mode. And obviously, as I said, since we are using single element, first mode is more accurate than second mode in terms of frequency and mode shape. And if you use the diagonal mass matrix, you got a little different value. Okay. And then also mode shape shown in here, and the mode shape similar to this one and that one. Of course, not identical, but similar to that. That's what you are going to get, two mode shape. So again, no zero eigenvalue. Okay. Now, if you compare that to exact solution, the exact solution is natural frequency is 12.4 and 485 square root of the angular frequency, 12.4 and 485. You can see that this is very accurate to this one, almost close to that one. Right? Using single element. Do you know why? No? Okay, that makes sense. That's why you are here to learn it, right? So if you remember what we discussed in chapter 8, for cantilever beam member to solve this one, when you use single element, we hit the exact solution, right? Remember that? Why? Was simply luck, or why we got the exact solution using single element for cantilever structure with the tip load?
Because the equation looks just like the one that you used to calculate deflection.
So the deflection equation of that cantilever structure with the tip load is exactly cubic polynomial, and which is the basis of the shape function. So in other words, your trial function can pick up the exact solution from there. Okay, that's why you got the exact solution. Then now we have this is the dynamic problem, not the static problem. Then how come you have very close to the solution of this one and that one? Again, in here, the reason is for this cantilever structure, the first mode shape. The first mode shape is very close to the static deflection shape of the tip lobe. All right, this mode shape is very close to the deflection of the cantilever structure. So obviously, the final element solution is going to be close to that one. Of course, in that case, it's not exact, but very close between the two. And also, you can see that the first mode is closer, but second mode is not that close. So if you are going to have an accuracy up to, let's say, 10 mode, okay, 10 natural frequency and 10 mode, then number of degree of freedom should be much larger than 10. Okay. In other words, that your maximum, you want to up to 10 degree of freedom, and you have a 20 degree of freedom like that one in the representation, then your higher mode shape is not going to be that accurate. So you have to have at least 100 or something like that. Then your frequency and mode shape is going to be accurate up to first 10 mode. Do you get it? Okay. So in mechanical engineering, there are generally three types of eigenvalue problem. Okay. One of the eigenvalue problem is what we talk about in here. Vibration is one of the typical eigenvalue problem. And then another eigenvalue problem is going to be a buckling of column. That's also eigenvalue problem. Okay. And third one is if you go into a little advanced class, then principal stress. You heard about principal stresses? So those principal stresses also are the eigenvalue of stress tensor or stress matrix. Right? So those are typically three eigenvalue problems in mechanical engineering. Any questions so far? Okay, then let's talk about the matrix condensation. We talk about this one also in chapter 3 to apply boundary condition. But here we are going to look at in a little different perspective. So if this is going to be static problem, again static problem, no inertial force, then if you're going to reduce size of the matrix, so you're going to eliminate, let's say, this column vector U2, what you have to do is from the second part of this matrix, K21 times U1 plus K22 times U2 is F. So you put this one, you put this one to the other side and pre-multiply the inverse of the K22 matrix, then you got, U22 is going to be shown in here. And then the first equation, this product is going to be this. So first equation is going to be K11 U1 plus K12 U2 is F1. So now you substitute this one into here. U2 is going to be replaced by that one. Then that's going to be this expression. That's the expression. And then now you rearrange this term. So the term associated with U1 put together. So this and then this product is going to be in here. And then those goes into the right side. So that now your matrix become smaller, okay, compared to original size. For example, this is 100, unknown. And let's say U1 is going to be 50, this is going to be 50. Then this matrix become, instead of 100 by 100, it's going to be 50 by 50 matrix in here. So this is going to be static condensation. And of course, static condensation is mathematically exact. There's no approximation. And sometimes we want to reduce the size of matrix, then we do that. But many times it's not that common. We don't do that kind of static condensation often. But the counterpart of the dynamic condensation has been more frequent in the past, especially computing power is limited. So if you're going to find the eigenvalue, finding this matrix, invariant matrix, okay, takes some time, computational time, but finding eigenvalue, eigenvector, it takes much more computational effort, okay? So just not invariant matrix, finding eigenvalue and eigenvector of that is going to be much more time consuming. So in that aspect, dynamic condensation happened to be much more popular, but with the advance of the more, fast computer technology, then nowadays some people do not worry about that anymore because you have, high-speed computer already at your hand, so you can use it. But anyhow, let's talk about this concept briefly in here. So dynamic condensation is, again, this is the standard matrixification. We have a sub-matrices, okay, associated U1 and U2. And in this one, there's no exact condensation for this dynamic, condensation, no exact. In other words, this condensation is exact, no approximation. Okay, this equation, that equation will give exactly the same answer. But here, unfortunately, there's no simple such exact condensation technique, so we have to do some approximation. So let's say I'm going to talk about this first, and then I'm going to show some example how we can apply that. So in here, let's say that any mass associated with the subscript 2 is negligible. Okay, so we ignore this. Then the second equation, this times that plus this times that is equal to 0 because this is going to be 0. this is going to be 0. So you got that one. Okay. Then from here, you put this one to the other side, and again, pre-multiply by inverse of the K22 matrix. You got U2 is going to be expressed in this manner. This is very similar to what we saw in the static condensation technique. So now you have this one. Then U1 and U2 is going to be written using this matrix T, defined as transformation matrix T. So U1 is U1, so this identity matrix, So U1 is U1, but U2 is going to be negative K22 inverse can K21 from here. That's going to be that. So this is the transformation matrix between two different vectors. Then your reduced dynamic equation is going to be your stiffness matrix, reduced stiffness matrix is going to be T transpose times original K, that's the original K matrix, times T. And this also T transpose times M times T, it comes from here, okay? So that's the reduced mass matrix, reduced stiffness matrix, reduced mass matrix, and then you can find the eigenvalue and eigenvector of that degree of freedom associated with the first group from this one. So again, this was 100 by 100. Now you split into half, then solving 100 by 100 matrix. Now we are solving 50 by 50. So which is going to be much more efficient in calculation of eigenvalue compared to that. Okay, then where we get this kind of expression is you can look at this one, the kinetic energy, like that, right? So this is 1/2 V. Okay, V is, we don't need the dot because V, and then M and V, and then potential energy KV squared, KX squared or KX squared. So this could be 1/2 X transpose K times X like that one. So if you look at that, that's why, transpose in front, and then same thing, 3, and then post multiplication like that one. So if you plug that, this expression into here, and then you come up with this one. So eventually the bottom line is that that's the reduced stiffness matrix, and that's the reduced mass matrix like that one. So this is useful when you have, some computational limitation solving the eigenvalue problem. But again, these days, this is less popular, okay, compared to some years ago. Then the explanation is how you neglect this just, degree of freedom mass here and here and here arbitrarily. Of course, you cannot just ignore arbitrarily, then you're not going to get the right answer. So one of good example I do this one is following sketch. I'm not very artistic, but I'm going to draw some tree. Some branches, and then small branches here, there, and then there are leaves. All right. Then I want to look at some motion of this one. When wind blow, then I want to look at what is going to be natural frequency of that one. So in other words, I don't want to have some kind of fall down of the tree in my neighbor. Actually, it happened to my house once. So I want to do this analysis, right? Then we are looking for the general motion. I'm not looking for those individual motion of the leaf or the small twig. That doesn't matter, right? So mostly I'm concerned about this major branch and some major, the trunk and major branches, right? The rest of them doesn't matter. And also the mass is going to be much smaller compared to that one, okay? So in that aspect, you can look at that in here. M1 is the mass of the trunk and major branches, okay? And those are the rest of them, okay? So then you can ignore those rest of them, and you can solve the problem a little bit quicker using this dynamic condensation technique. However, sometimes the problem is not clear whether I can condense out some degree of freedom or not, then you better not do that. Okay, just leave it alone and then do the calculation, even it takes some extra time. But if you're sure, I know this, so I want to really save time, my computation, then you can do that. Right? So some program has an option for dynamic condensation. And some program doesn't have no option like that, and so it depends on the nature, but at least I'm going to talk about this one. Any question? Okay, then we talk about eigenvalue problem. Then we are going to talk about now the transient problem. Okay, in other words, we are going to find the transient motion of the beam or structure. So equation of motion is given in general manner, m d double dot c d dot plus kd equal f. Okay, d could be u in notation, but here we use d. So we have to solve this simultaneous equation of the ordinary differential equation but second order. And you have to find the solution as function of time. How you do that? There are different ways of doing that. Then the first question is, we learned backward and forward different technique previously. So can you apply that technique to here or not? If you can apply that, that's great. And if you cannot, then you have to have also new technique to solve this problem. So the first question is, can you use that forward, backward, or Crank-Nicholson method to solve this second order differential equation? What do you say?
Confused what?
Can you use the previous forward, backward, or central difference technique, Crank-Nicholson, to this second order differential equation? That was first order differential equation, right? And this second order. No, no way. Be optimistic. Answer is yes. Answer is yes. Then how? You can transform this equation a little different way. So in other words, I define V as d dot. Okay, like this displacement d, V is velocity, right? Then this equation is m v dot, right, plus c v plus k e is f, right? Correct? So if I can put this one, d dot minus v equals 0, right? Then I can put this two equation into set of equation. So v dot, d dot. Then this is going to be m 0. Okay. So let's do this equation first. And then v and d like that. And this is going to be c. And this is k, right? So m V dot plus CV plus KD equal F, right? And second equation give you that from here, D dot, so this is 0. This is identity matrix. D dot is equal to V. So that's going to be identity matrix, and this is 0, right? And this is 0. Correct? Then I can call this going to be X dot X. So just first order derivative of the equation. Right? If I call this is A, E, C, like that, then that's going to be first order derivative of the equation. That means we can apply forward, backward, or central difference technique to this one. Okay, that's why many program, for example, MATLAB, they provide the routine for solving first order differential equation, but they sometimes do not provide the high order, second, third, fourth order differential equation, because you can always formulate that into first order differential equation like that. Then what's the drawback? Drawback is that the size of matrix become double, right? So this was 100 degree of freedom, then this is going to be 200 degree of freedom. So larger, right? But technically, you can solve this one using central, forward, or backward different technique we learned previously. Right? Got it? Okay, so at least you have some, baseline. I can solve that problem using the solution technique we learned previously. That's good. Okay, but now we are going to learn different technique too, because mostly in finite element, formulation, they don't use this one. Okay, usually for this kind of formulation is some kind of the stability problem or the dynamic stability problem. Some they use this kind of equation for that one. But in finite element formulation of solving this dynamic equation, they usually do not use this kind of the formulation. They just want to solve with this one directly. Okay, in other words, they don't want to increase the degree of freedom from original problem of the twice of that original problem. So what technique do they have? There are a couple of some representative technique, and one of them is so-called, again, central difference technique. Central difference is also one of the most popular, and that's one of the most popular technique in here. So we are going to do central difference in time in here. So here, if this is going to be time axis, then t plus delta t and t minus delta t, then acceleration at here at time t is this one. Have you seen that one, or you want me to develop this equation? Let's start with this one first. Velocity here is in central difference technique. This minus that divided by twice of delta t, so 2 delta t. Right? Make sense? Now, what about acceleration in here? Acceleration here is we used t delta t over 2 and t delta minus delta t over 2. So we calculate velocity t plus delta t over 2. Then what is this one? T plus delta t minus dt divided by delta t, right? Correct? Now, we do same thing for here. Velocity t minus delta t over 2 is now t minus delta t over delta t, right? Correct? That's the central difference between the two. This is central difference between the two. That's the velocity in here. Then what about acceleration at t here is d dot t plus delta t over 2 minus velocity t minus delta t over 2 divided by delta t, right? This velocity minus that velocity divided by delta t is equal to acceleration here. Now, if you plug this here, d t plus delta t minus dt delta t minus dt minus dt minus delta t over delta t over delta t. If you simplify that, that's going to be exactly the same as this one. Okay, so that's second order derivative. That's the first order derivative. So far, so good. Now, then what you have to do? You plug this one into here. You plug this one into here. That's simple mathematics. So plug that into here and plug that into here. And then what we do? As usual, we have to rearrange. So a known term on the left side, known term on the right side. So a known term is always the future solution. So t plus delta t is going to be unknown, to be determined. So this comes in here, and the rest of them goes into the right side, just rearranging that. Huh? So eventually this is going to be a times dt plus delta t is something b, like this kind of format eventually. So we are solving for this one. Okay. However, one thing you notice in here is that when you say delta, t equals 0, when you say t equals 0, so I want to find solution at delta t. Yes. Oh, the light. Where is the light coming from? I don't get it. Some spots. Better. Thank you. It's weird. Where this some overshape of. All right. So here, when t equals 0, then delta t 0. So t equals 0 is that initial condition, no problem. But this one, negative delta t. So negative delta t doesn't have physical meaning because everything starts from 0. So before delta t, no physical meaning. But unfortunately, we need that. I cannot simply ignore that one because this is mathematically existing term, right? So we have to deal with that one. What could be negative delta t? So that's what we are going to talk about in a minute. And secondly, if you look at this term, I have a mass term, damping term, okay, but I don't have stiffness term, right? I don't have stiffness term. So if you don't have stiffness term, means this is going to be unconditionally stable. So in other words, delta t have to be small to control the stability. Okay, that's what you can see there. All right, then going back to the question that how you calculate, solution negative delta t. Again, we cannot just, make it arbitrarily, which is going to affect the solution. So we cannot do that. So what you have to do is going back to here, we are going to find the solution mathematically consistent from the formulation. So when put t equals 0 here, right? And then you find this one, so this is going to be d negative delta t, and multiply by this one delta t squared, and put everything to the other side. That's going to be this equation. This is what I'm talking about. So multiply by delta t squared, so which is gonna be this times that, and then move this one to the other side, which is gonna be this one. Okay, so this from the acceleration, and from velocity. Also, if you set t equals 0, okay, then this 0, this delta t, negative delta t. So put this one here and the rest of them to the other side. So this times 2 delta t plus this. So this is going to be like that. Okay. So in other words, this is exactly the same expression when t equals 0 from here and here individually. And then I substitute this one into here. Okay. Then what do you get? You get this expression. So this is we call fictitious solution. It's not the physical meaning, that doesn't have physical meaning, but mathematically, this fictitious solution, negative delta t, have to be based on that one to be consistent with the formulation, our formulation, okay? If you just use arbitrary number, then that is going to affect your solution. All right? Time-dependent problem, one of the nature is that solution in the previous time is going to affect solution in the future. So whatever you put wrong input in the beginning, that is going to scrap the whole solution after that. That's the nature of transient solution. Okay, so you have to start with the right solution. That means this fictitious solution, you cannot just put arbitrary because it doesn't have physical meaning. So you have to look at this one consistent with the formulation mathematical consistency. You have to put that on, then that's going to be your fictitious solution. You got it? So then what is the solution procedure? The initial process is that you compute the mass, damping, and stiffness matrix. And again, damping matrix, mostly you are not computing, but you are, from some your measurement, or if proportional damping, then that's going to be linear combination of mass and stiffness. So you do that. And then by solving the initial dynamic equation, okay, so you calculate initial acceleration because initial condition is going to be initial velocity and initial displacement. Those are given and initial condition. So from there, you calculate initial acceleration from here. And then you are going to find this fictitious displacement, this value, the one time, then you calculate that from here. Then now we are going to do this calculation over and over. So you have to calculate this one once, okay? You have to calculate those effective mass once, right? Then after that, we are going to repeat the calculation over and over. So in other words, you said repeat this one over and over. What do you mean repeat this one? You have to calculate this component, the right-hand side column vector, this one. It's going to be log of this one. So initially when t equals 0, you need fictitious time. But after that, I already know the previous two solutions, so we can continue the calculation, every delta t. Only the first time I need a fictitious solution. So this one required two previous time, solution at two previous time, 0 or negative delta t. After that, now 0 and delta t, then you can calculate 2 delta t, and same thing, 3 delta t like that. Okay, so then just embodying this matrix, you can calculate the new solution. And then once you have the new solution displacement, then taking those standard acceleration and displacement velocity formulation, you can calculate acceleration and velocity at delta t, okay, or t plus delta t. So you can continue this one over and over. Got it? But this technique, as I said, you need solution at two consecutive previous time, t and t minus delta t. So that's why we need fictitious solution to start with. Yes. Then, what is the characteristic of this solution? This solution is, as I mentioned, unconditionally stable. I mean, conditionally stable. Sorry, conditionally stable. Conditionally stable. So, in other words, your delta t have to be controlled to maintain stability of the problem. So, time step size must be controlled from this equation. Or this equation, this is going to be the period, and that's going to be the angular frequency. So what do you mean? If you have a matrix, mass matrix, stiffness matrix like that one, then you calculate this value and pick the largest one. And then if you plug in here, delta t have to be smaller than this value. And again, if the C matrix is going to be 0, then that's going to be explicit. Okay. So if you want to solve this problem, so in this case, the damping term is ignored in here. If you want to solve that problem, and then initial condition is given here, and bound condition is already applied, so we don't have to worry about bound condition, but initial condition is given here. Then we are going to apply central difference technique. So we need to find the smallest, period or smallest, largest circular frequency. So k minus m square m, as we did in the previous, example. So we solve that one. Then we are going to have a two eigenvalue. What is the eigenvalue? Is going to be this. Okay. So largest one is going to be that one. That's the largest one, right? So plugging here, 2 divided by, now square root of 5. Of course, we pick only parts to 1. Then you got this value, 0.891. So delta t have to be smaller than 0.891. Larger than that, then your solution is going to be unstable. So solution blows up. What does it mean? There are examples here. So when you pick delta t is 0.28, smaller than that, I still don't remember why I picked 0.28 rather than 0.2 or 0.3. Okay, but anyhow, so we have already this matrix. We don't have to worry about it. Now, from the dynamic equation, we know that initial condition. We calculate the initial acceleration. So initial acceleration is going to be this. Okay. This mass and this the F minus K times initial velocity, initial displacement. So you got that. Then we calculate the fictitious time from those initial velocity, initial displacement, initial acceleration. We got that. And we calculate the effective mass. In this case, we don't have damping terms, so only the mass term is going to be, used in here. So that's the effective mass. And the right side column vector is basically following this expression. Plug into here, except that C is going to be 0 in this case. So plug into here, that's going to be F, that's going to be K, and 2 minus 2 about delta T square mass matrix, and time T equals 0 is initial condition. And then this again is equal to that mass matrix, and damping term is 0, and that's the fictitious solution is here. So F is going to be shown in here. That means now you solve this matrix, then you find U1 and U2 at delta T, which is going to be 0.28, and you get that one. Then you continue to calculate this one over and over for every delta T of the F. Repeat same thing. and then you find solution, then you get that. So this is going to continue over and over. And once you find displacement, then this you can calculate acceleration and velocity from this central difference technique. So nothing new in here. However, this technique, if you are not interested in velocity and acceleration, you don't have to calculate that. You just simply calculate displacement all the way from 0 to the final time. But most cases, you are interested in velocity and acceleration, so you need to calculate that one also every delta t2. So that's what we are going to do, in computer program over and over. So far, so good. Now, if I pick the large delta t, 28, much larger than critical value. The reason I pick larger value is going to be, I'm going to show you that this is going to explode very quickly. Then the fictitious solution is going to be from here. If you plug delta t, you got that. That's the fictitious displacement. And then effective mass is going to be shown in here. And F0, the column vector is same thing, except that now this is going to be, delta t. So you got this value, right? This is also the fictitious displacement. You got that one. And if you solve this equation just for delta t, you can see that displacement at initial delta t, 28 second, whatever you need, then you got 0 and 38.15. All right, very large number. And then if you do one more calculation, one more step of delta t, exactly same thing, just substitution. And then again, solve this matrix equation, AX equal B type, then you can see that now this is going to be million or even more than million in here. So you can see that solution blow up very quickly. So after 3, 4, or 5 computation, then they are going to say infinite or not a number, the program is going to stop. Okay, so that's what I'm talking about, instability. And if you pick this one, closer to your critical value was 0.89, 891. So if I use, for example, 0.9, okay, if I use delta t 0.9, then what happens? It's going to blow up very slowly. So first 100, 200,000, you may not see the blow up. But as continue calculation, million times, then eventually you see that solution blows up. Okay. In other words, that if this is going to be the vibration problem, then you have to go up and down like that on. But as you continue, never coming down, it just continue to increase the displacement, then means solution blows up. Right? So depending on how close your delta t to the critical value, the speed of that blow up is going to be fast or slow. Right? So critical value, I mean, your delta t is much larger than critical value, like what you see in here, then it's going to blow up very quickly after small number of calculations. You got it? So for conditionally stable algorithm, you have to make sure that your delta t is going to be small enough, then the critical time steps are. All right, let me stop here. Today.